This note-taking guide today is on chords. If you guys remember, the chord of a circle is a line that touches both edges of the circle. So this right here is a chord. What's this right here from the center to the edge? It's a radius, right? If I had the diameter there, though, it would be a chord also, right? Because it touches both edges of the circle on the inside. So we have some rules about chords that we're going to go over today, and then see if we can do some math with them. So the first rule says this: chords that intersect the radius. So if you have a chord and it intersects the radius, it also always intersects at a right angle. And the radius bisects the chord. Does anybody know what bisects means? Breaks it into two equal pieces, right? So if this radius goes through the chord, it breaks the chord into two equal pieces, and it intersects it at a 90-degree angle. That's rule number one, okay? Another rule says that if you have the diameter, then the diameter of a circle is perpendicular to the chord. So again, meaning that it forms 90-degree angles with the chord, and that the diameter bisects the chord, which means it cuts the chord into two equal pieces. It also cuts these two arcs into two equal arcs, okay? So if you know the length of this arc, then you know that you also know the length of this arc because it got broken into two equal pieces. So really this second rule and the first rule, they're about the same rule because a radius is half of the diameter, which means these rules follow those same rules over here, okay? Next rule. In a circle, two chords, if they're equidistant from the center of the circle. So see how this one is marked the same length away as this one? So if you draw two chords that are equidistant from the center of the circle, then the two chords are equal in measure, okay? So this piece here on this chord is equal to this chord over here. So each chord measures the same if it's equidistant from the center of the circle. And then the last one says, in a circle, if two chords are equal in measure, then their corresponding minor arcs are equal in measure. So we know that LM equals XY, which automatically makes this minor arc from there to there congruent to this minor arc from here to here. So if the chords are equal to each other, the minor arcs are equal to each other, okay? Those are the rules we're using today to do some math. So let's see what we've got here. Number one says find the length of QS. So I want to know the length of this chord from Q to S. I know from the center to the edge is 11. So what do you know the whole length of QS is going to be? 22. Because exactly, because it bisects it, right? The radius bisects the chord, which means it breaks it into two equal pieces. So this is 11, this is 11. So QS has to be equal to 22. Nice job on that, you guys. Okay. Next one then, a lot of stuff going on here in this circle, but it says to find X. It says the length of this chord is 6x minus 5, and the length of this chord is 13 plus 4x. Now, we had a rule that said if our chords were equidistant from the center of the circle, then the two chords would be equal to each other. Do you guys see how this chord is 18 away from the center of the circle? This chord is 18 away from the center of the circle. So what do I know about the length of the two chords? They're equal. So I get to go 6x minus 5 equals 13 plus 4x. So I'm really just going to solve that equation now to get x by itself. So what do you want me to move first? 4x. The 4x. So we're going to subtract the 4x over to the other side. When we do that, we get 2x minus 5 equals 13 because the 4x's cancel over there like they're supposed to. Next step. Yep, add the 5. So I get 2x equals, one more. Yep. And then last step,
Divide by 2.
divide by 2. So x equals 9, because 18 divided by 2 is 9. Okay. So again, the reason that rule works is because we have that rule that says if the chords are equidistant, meaning the same distance from the center of the circle, then the chords are equal to each other. Anybody have questions on that one?
Is there any instance where it's not going to be equidistant?
Well, you'll clearly see some chords sometimes that are not equidistant from the center of the circle. But I think for today's purposes, for the most part, we're going to just be working with the ones that follow the rules. Okay? All right. State what you know from the picture. So this is an interesting picture to just think about and to state what we know from it. But this for sure is a diameter, right? Because it goes through the center of the circle. If it's a diameter, what do you know it did to the two pieces of the chord? It bisected it. Bisect means break it into two equal pieces. So do you know some pieces that are equal here?
A and B.
Yeah, so let's go to the middle though. So A to D is congruent. Oh my gosh, my congruent sign is funky. Sorry.
Okay,
So AD is congruent to DB. We know that those measure the same because they are bisected by that diameter. Do you know anything about anything else? So that's a good question. If this arc would be the same as that arc, they probably would be the same, right? Although our rule did not tell us that on that. I guess I take that back. They did say that up here on this diameter one, right? I was thinking we were looking at that radius over there. But we did say that this arc would be the same as this arc, right? They're marked the same on here. So we can say that the arcs are the same. So tell me which arc measures we don't have a letter over here, do we? So if we have A, B, C, D, maybe we could call this one E. But we know that arc AE would be congruent to arc EB. Okay, and we know that just from that rule that we had up there about the diameter. All right, we also know that if we wanted to, we could say that we know that this is a right angle, this is a right angle. Those are all right angles around there, right? Because of the way that they're perpendicular to each other. All right, let's look at another example. Let's label what they give us, and then let's see if we can figure out what they're wanting us to do here. So it says ZY equals 6. So from Z to Y, this whole length right here equals 6. So maybe I'll just go like this so we know it's 6. Okay. Before I even go any further, I kind of think I might want to say that this is 3 and that is 3. Would you guys agree with me that that might be something that they want us to look at? So I'm going to label those 3 and 3 just because I know that that's what that happens with that diameter. All right, now XW is 4. So from X to W, I know that's 4. And it says find XY. So I'm really glad I labeled that 3 because guess what I formed right here that I need to be looking at? A right triangle. How do I find the hypotenuse on a right triangle? I do the Pythagorean theorem, right? A squared plus B squared equals C squared. I'm looking for the hypotenuse, so I'm looking for C. So I'm going to go 4 squared plus 3 squared equals C squared. And I'm going to solve this for C. So 4 squared is 16. 3 squared is 9. 16 plus 9 add together to be 25. Square root that to get C by itself. And what's the length of C? 5. Thank you. Okay. So that was helpful that I just broke that into 2 pieces that I knew right off the bat, right? Because then it made it easy to see that I had 2 sides of that right triangle there. Are there questions on how I found that? All right, here's another example then here. This one doesn't have a chord in it at all, does it? So today's rules not applying here. This is actually a tangent, so this is one of yesterday's rules. Are you guys following me on that? The tangent and the radius. Anybody remember what happens with the tangent and the radius?
Form a right angle.
They do form a right angle right there. And so if I want to find my x value here, I have to think about some rules I haven't used for a little while. Okay? I know this angle, so I'm going to go from this angle right here. And this would be the opposite side from that angle. This would be the hypotenuse over here. And this would be the adjacent side from that angle. Do you guys agree with me that that's how I would label my triangle? Does anybody remember a rule that uses the opposite and the adjacent?
Tangent.
It is the tangent. So I'm going to use that rule. Up there on the board it says the tangent of the angle equals the opposite over the adjacent. And do you remember how we just substituted our stuff into that and cross multiplied? That's exactly what we're going to do. So the tangent of what angle? 60 equals the opposite, which is 21, over the adjacent, which is x. Put a 1 underneath there and cross multiply. So on your calculator, do the tangent of 60. And it gave me a square root, right? Do you guys remember how to get a decimal point number? You hit those arrows right above the enter sign. So we can say that's 1.73, and that would be times by x. 1.73 times by x, and then this other direction it equals 21. And how do you get the x by itself? Divide. So divide both sides by 1.73. And what's the length of our side x? Anybody?
69.94.
Oh, I got 12.14. Anybody get that?
I got it the second time.
Okay, thank you. Thanks for checking. All right, so I guess the point on this problem is to remind you that the rules that we've used with right triangles still apply. You can still use all the right triangle rules that we've learned when you're looking for the missing side, okay? And what we did was we actually found the length of the radius this time, right? So our radius is 12.14 in length. All right, last problem. We have to draw it out ourselves. It says if a chord is 6 inches from the center of a circle. So I have a chord 6 inches from the center of the circle. So you guys following me with how I can draw that chord? Okay. And it says that the diameter is 20 inches long. I'm going to draw my diameter in a really special spot because I need it to help me, okay? Do you guys see that if I drew my radius right here, I'd form a right triangle? So I'm going to draw my diameter through there so that it's still